Så. Ja, tack så mycket. God förmiddag och lite senare än förväntat, men vi gör vårt bästa här och välkomna till det här seminariet. Jag heter Björn Halleröd och är huvudsekreterare för forskningens infrastruktur över Vetenskapsrådet. Och vi har då ett seminarium idag som har titeln Varför behövs stora forskningsanläggningar? Och jag utgår ifrån att de som jobbar med de stora forskningsanläggningarna har ett svar på den frågan. I alla fall för dem själva. För oss andra så är det ju också en fråga om är de värda pengarna? Det är stora investeringar. Hur skulle de här investeringarna se ut på något annat ställe i forskningssystemet? Och hur får vi ut den bästa nyttan av de stora åtaganden som vi har gjort och gör i Sverige? Och det är ju inte minst då viktigt från en svensk horisont nu. Vi är värdnation för ESS. Vi har byggt Max 4 och vi är aktiva i många av de stora europeiska anläggningarna. Både inom de här områdena då som rör ljussynkrotroner, frielektronlasrar och neutroner, men också andra anläggningar som stora teleskop och så vidare inom ESO till exempel. Och gårdagens Nobelpris kommer just från en sån anläggning, åtminstone delvis. Då, anläggningen ESO och Very Large Telescope. Vi har bjudit in 3 stycken forskare som använder då ljussynkrotroner, frielektronlasrar och neutronspridningskällor i sin forskning. Och de 3 kommer då hålla ett kort föredrag här om sin forskning. Och först ut då är Filipe Maia. Och han är då Associate Professor in Molecular Biophysics with Specialization in Coherent Imaging with X-ray Lasers. Och han är verksam vid Uppsala universitet, men jobbar då mycket mot X-anläggningen i Hamburg, som Sverige då är delägare och aktiva i. Och så har vi Martin Månsson, som är professor i Neutron Scattering vid KTH. Och har också spenderat mycket tid vid PSI i Schweiz och också ETH heter det va? I Zürich före det. Och nu leder Martin den svenska neutron, vad heter den? Ska vi se, Swednes. National Graduate School in Neutron Scattering. Och till sist har vi då Elisabetta Nocerino som är PhD-student också vid KTH. Och också arbetar med neutronspridningsanläggningen, Neutron Scattering. And now I switch to English completely here because Elisabetta don't speak Swedish, don't really understand Swedish. Okay, sorry for that. Whereas Filipe understands Swedish but don't speak Swedish. If you're not forced, then we're not going to force him. I can also tell you that, which I learned that Elisabetta speaks ancient Greek and Latin. And of course, Italian as a native tongue, but you promised to stick to English, I guess.
Absolutely.
Yep. And as I said, you will have a short presentation. It will be about 15 minutes to present your research, and there will be 5 minutes for questions. And I think when you ask questions after the talk, try to ask the specific questions then, because then afterwards we will have a panel session, and then we can have more general discussion about the pros and cons with the big research facilities. So, and we will have half an hour for that before we close the seminar. So welcome to you all, and especially welcome to our talkers, and I give the floor to Filipe.
Thank you very much. Let's see if we can do the sharing of the screen. Okay. So I will talk about XFEL science in Sweden. And first let's try to understand what are X-ray free electron lasers, starting with the X-ray part. So X-rays are just part of the electromagnetic spectrum with wavelengths of about 1 angstrom, 10 to the minus 10 meters. And that has important consequences. So one of them is that they have energies that match the electronic energy levels of several atoms, and so can be used to probe electronic states. And the other important consequence of their wavelength and energy is that the wavelength matches well the interatomic distance in molecules, so we can use to probe the structure of molecules. And this has led to 40 X-ray related Nobel Prizes until now. So how do X-ray free electron lasers work? Well, they work in a similar way to previous sources in the sense that we have a bunch of electrons which wiggles through an undulator, and as they go through this undulator that you can see in the picture, they will accelerate, and then they will give off light. The particular which is different compared to previous sources is that this light then will also interact with the electrons and causing them to microbunch into different slices, and this has an important consequence. While in a previous generation light source like a synchrotron, the electrons are randomly distributed, and so the amount of light that we get is simply proportional to the number of electrons. In a free electron laser, you can see that the electrons are bunched into certain slices, which are separated by just a multiple of the wavelengths, and the amount of light we get in the end is going to be proportional to the square of the number of electrons and not simply the number of electrons. And this will give us a huge boost in the amount of light that we get out of those electrons. So while we can have 10 electrons tightly packed behaving as if they were 100 times, giving 100 times more light than a single electron, like a giant particle. And this is the principle of the self-amplified spontaneous emission, SASE. So how can we describe the power of the free electron laser? Well, if you take all of the sunlight that hits the Earth and if you focus it to 1 square millimeter, that is about the same power density, peak power density, as you have from a free electron laser when focused with spot size, which is about 1 square micrometer. So it is a huge amount of light and power that we have. And it corresponds to a 10 billion-fold increase compared to previous synchrotrons, or to previous X-ray light sources, which were synchrotrons. There is another important difference, which has to do with the pulse length. So if you compare the pulse length of a free electron laser to 1 minute, that ratio is the same as 1 minute compared to the age of the universe. So we have pulse lengths on the order of femtoseconds, an imaginably small amount of time, and so short, in fact, that we can use it to probe atomic motion. It's that quick. And this has already was proposed in the 2000s, in fact, by a Swedish team. The idea of using these short pulses to outrun the damage that radiation causes in matter. So if we use a very short pulse and shine it on a sample, we should be able to look at the scattering, the signal that comes out of it before the sample explodes, and so use the difference between the speed of light and the speed of the shock wave to obtain basically undamaged structures. And this has been called diffraction before destruction. Another example of pioneering Swedish science is the first demonstration of this idea in practice, because the previously was just a theoretical approach, and then in 2006 this was proved experimentally with an artificially made sample where the first shot showed one diffraction pattern, the second shot a completely different one, and that's because the sample was completely blown into pieces by the first shot, but yet from the diffraction pattern of the first shot we are able to reconstruct a sample which matches what we had acquired before the experiment using a scanning electron microscope. Exactly, actually. It shows no damage whatsoever, proving the idea that diffraction before destruction is possible. And then we carried out doing more science, now going to the LCLS in Stanford, the first hard X-ray free electron laser, and this is showing an example of imaging viruses in flight, a Mimi virus, a very large virus, which was captured in flight by the X-rays, and the X-rays diffracted, gave rise to this beautiful diffraction pattern, which then can be phased, and we can obtain the two-dimensional projection of the virus. And this was published in 2011. In the same year, actually very close to about the same time, a different experiment was done where crystals were again intercepted by the X-ray laser, and these were not ordinary crystals, these were nanocrystals, much smaller than what were previously used. So one of the difficulties when crystallography is growing large crystals, and here we have nanocrystals of photosystem 1, part of the photosynthetic complex, and they were flown across the X-rays. The diffraction pattern was collected and phased, obtaining the structure of PS1, a membrane protein, and important for photosynthesis and understanding carbon cycle. Another important highlight, This one looking at the structure of water. What happens to supercooled water? Water has many interesting properties, and in this case, the experiment was shooting droplets of water into the beam, and they cool down as they cross, as they go through vacuum by evaporation, and so we can probe the water at different temperatures and look at their structure. And the interesting thing is, when does ice start to show up? And this happens very quickly when water is supercooled well below the freezing point. And this is what this, again, Swedish team managed to observe in 2014. And it was, in fact, the cover of Nature of that edition. And here we have an example of a molecular movie of bacteriorhodopsin, which is a membrane protein, which is a light-activated proton pump. So when you shine light on it, it can actually carry protons across the concentration gradient. And in this example here, the researchers were able to take a movie of this happening by shining a laser, and then after the laser shining the X-rays, and then obtaining structures at different time points. In this case, we have 4 different time points, and we can look at this huge protein in motion, seeing what it does in atomic detail. One more example of the photosynthesis. In this case, this was taking advantage of the fact that because we can outrun radiation damage, we do not need to freeze the sample like it happens in traditional crystallography. In this case, we're looking at the photosynthesis, photosynthetic complex photosystem 2, and doing this at room temperature and comparing to cryocooled. And you can see that there are important differences which actually matter for the mechanism of the photosynthesis. So what are the opportunities that I see in the future from the European XFEL? So we have, on the technological side of view, we have fast increasing repetition rates, multicolor experiments, shorter pulses, and higher peak power. So these will all lead to new and more imaginative experiments, which I believe we haven't even thought of, all of them. And also we have much more reliable instrumentation. Until now, things have been developed, and now they're getting into a point where they are starting to be more stable. And so we are able to do more complex experiments because we can rely on it. From an academic point of view, we have now a generation of XFEL pioneers here in Sweden, which are coming of age, which have started their experiments 10, 15 years ago, and are ready to take advantage of these capabilities. And this, I think, is pretty much unique in the world, that we have so many as here in Sweden. We also have the ability to produce strong international collaborations at Free Electron Lasers, because often experiments are done in large collaborations, and it naturally leads to the creation of these strong bonds between different researchers. And also, because of the large collaborations, this tends to be interdisciplinary work. On the scientific side, we're starting to see, given the high peak powers and short pulses, great progress in nonlinear X-ray physics. And actually, just from a few weeks ago, we have this paper on photorecoil imaging, looking into stimulated Raman scattering, X-ray Raman scattering. Again, with Swedish contributions. This was done at the European XFEL in just a completely new way to look, try to detect the Raman scattering, stimulated X-ray Raman scattering. Quantum optics also taking advantage of the short pulses. There are ideas, for example, on how to use fluorescence to obtain structural information. Using the circular polarization, which are now available at FELs, one can look at the ultrafast magnetism and other solid-state physics ideas, ultrafast chemistry, like I showed in the case of the photosynthesis, and catalysis, very important for the fuel sources of the future, and carbon sequestration, for example. And this is a more basic example of the radiolysis of water, looking at the first process as you have radiation heating a water molecule and the electron jumps out, what happens immediately after to that cation. And this again was published this year. Also, the idea of single molecule imaging. Now that we're reaching these really high intensities and short pulses, how far can we push this? And finally, also time-resolved crystallography. So until now, most of the time-resolved crystallography experiments were being done on light-sensitive proteins, but we'd like to extend this to all kinds of proteins. And I think photo-cage reagents would be a possibility to extend this to all kinds of reactions, as only a very small amount of proteins are light-sensitive. And all of these are areas with strong Swedish community. And to show this, I can like to point out, for example, to the Gregory Aminoff Prize given by the Royal Swedish Academy of Sciences just a few weeks ago, to, among others, Janusz Hajdu, for their work on the development of structural biology for X-ray free electron lasers. And also, there are several ERC grants given to people working on XFL science in Sweden. Thank you very much.
Thank you, Filipe. So I was a bit unsure now, but we don't have any questions from the audience. No, okay. So then I will ask you one question.
Yes.
Imagine that I were a politician. I have the budget. I have two main problems that I now need to solve. I have the climate change, and now I have a pandemic to solve. So how can you help me? How can you help me with XFL?
So X-ray free electron lasers have already been used, for example, to study COVID. Looking at, in particular case, I know of an experiment at the LCLS, but I know that the European XFL is also working on COVID-related proteins using 0.5 femtosecond crystallography. And this is definitely an area which is going to be important, and also be able to look at the reactions, not just the static structures. So being able to look at this in a time-resolved fashion is going to be important to be able to push this forward on the side of the COVID research, and on the side of other pandemics, of course, would be the same thing. In terms of the climate change, I think, for example, looking at photosynthesis is extremely important, because if we understand how nature makes this amazing reaction, we might be able to replicate it and also try to, for example, create more efficient ways to generate hydrogen-based fuels, or create fuels using the sun as a source of energy. But to do that, we really need to be able to understand first how does nature do it, such that we can try to replicate it as best as we can, or try to harness its power.
And currently, you need a free electron laser to do
so
that.
Because a lot of these things happen at fast timescale. For example, photosynthesis, these reactions happen at picoseconds or femtoseconds, even the initial ones. We need something which enables us to take a flash of things as they happen, and also these things happen at length scales which are on the atomic level. So we need to be able to have some probe which allows us to probe that atomic level. And currently, the XFEL is basically the only thing that allows us to do this.
Okay, thank you. Okay, as I understand, we don't have any further questions from the audience, but I think you will get other questions later. So sure. Thank you very much, Filipe. And then I leave the floor to Martin. Yeah, okay. No, okay, sorry. I give the floor to Martin.
Or maybe we have to stop sharing also.
Did you hear us, Martin?
So, if anyone is saying something to us, we can't hear you.
Do you hear me now?
Do you hear me now?
Now I hear you.
Okay.
Unfortunately, we didn't hear the talk or the questions, but...
Okay.
Okay.
But, you know, repetition is the mother of learning, so maybe.
Okay, so one more
time.
time.
Really good.
So, but anyway, I give the floor to you, Martin, and we see if you are unique or not.
Elisabetta couldn't hear you also, so I think this is something. Okay, you can hear me at least, I hope.
Yes.
So, thank you for inviting me to give this talk. I will focus a little bit on the broader picture, and then Elisabetta will follow up on science. So this is a picture from our last Swedish Neutron Week last year, where we were 124 participants, so big group. So this is what it's all about, right? I mean, the European Spallation Source, the investment. And of course, this is a huge project. It has a big budget, 1.843 billion euro in the construction budget, and it's a European infrastructure project, right? And of course, about 37.5% comes from Sweden, but of course, the rest comes from Europe. And the same for the running costs, where Sweden is estimated roughly to pay 10% running cost, and the rest of Europe will pay 90%. These are approximate numbers, just for having a rough pictures. And I mean, as I see it, of course, this is, of course, a facility that will stay permanently in Sweden. No one will ever think about moving ESS. I'm pretty sure about that. And this is clearly an investment from Europe in Sweden. So this is my kind of view on things. And of course, with that comes all the benefits of having such a source in our country. So why large-scale facilities in general? Of course, you have very great in-house laboratories that you can do great things with. And I mean, the main thing is, of course, that large-scale facilities are really the best experimental tools we have available. So this is like, I say, a Trabant versus a Koenigsegg, if you like cars, at least especially for in-house neutron laboratories. The other thing is that a modern neutron source is not just one tool, it's an entire toolbox. So not only the experimental tools, but also the computing and modeling resources and so on. So this is, of course, a very big difference. And to really take the next step, let's say, in technology and science, we are now at the point where we need to use these kind of tools. Another big difference is the large-scale facilities is really focused, I would say, close to 100% on doing high-impact science. So this is 24/7, right? People work around the clock. And every single experiment that you do there is usually peer-reviewed, which is definitely not the case for your in-house experiments. So it's harder to access, but on the other hand, you choose, let's say, the best experiments to do there. It's also a dynamic ecosystem that changes every week. So every week you have new users, or even every day sometimes. And world-leading scientists from all fields meet at this facility every day. So the ESS plus the MAX 4 is, of course, a breeding ground for high-impact science and technology industry, but also for ideas, networking, PR, and politics and stuff like that. So it's many layers of this onion. So I'm here to talk about neutron scattering, and I have one slide for those of you that might not be familiar with it. So neutron, this is a subatomic particle, so it's very small, without charge, so that's why it's called a neutron, it's neutral, and the magnetic moment. And when they interact with atoms in a material, it interacts both with the nucleus, the nuclei, as well as the electrons of this atom. And the electrons, they have a spin, which is basically the small magnets of the material. So you have an interaction with both the atomic structure and the spins and the magnets. And this is basically how you do a neutron experiment. You have some neutron source, in this case ESS. You have a neutron with some initial state, which means the direction of the neutron and the speed of the neutron. And this you set with a knob on your instrument, basically. The neutron is shot into your sample. Here it interacts, so this right picture here, in the so-called scattering process, where it changes its direction and potentially also its speed. And then you detect the outcoming neutrons, the final state, with your neutron detector. So this is 101, how you do. And if you only detect the change in direction, this is called elastic neutron scattering. So only the direction or angle is measured. Then this tells us about the static structure. So where the atoms are sitting and how the spins aligned in this material. If you also detect the change in energy when it interacts with the system, it can give or take energy from your material. We call it inelastic neutron scattering. And this tells us about dynamics. So what are the atoms doing? Are they moving? Are they spin rotating or flipping? So this is atomic structure and dynamics plus magnetism. And if this is, a little bit complicated picture, at least you should take home this message, that basically we have a neutron source, which is the guy with the pool cue. And then we have the neutrons, is this white pool ball. And then we have your sample material here. And even though I didn't hear Philip, I'm sure he talked about that he destroys his sample. So if you want to do this at home and try your neutron experiment, then you have to, of course, super glue these balls into your pool table, because otherwise you destroy your sample. So that was Neutron 101. But why should we use them? So there are many benefits of using. And I might refer to this as contrary to X-rays, but these methods are, of course, highly complementary. But I'm here to talk about neutrons. So one of the main benefits is that you can detect light elements because you scatter from the nuclei and not from the electrons for the structure. And this means that you can study hydrogen, oxygen, lithium, light elements that are very difficult to see with X-rays, actually. And this means that you can, for instance, see water. So this is the ground for all life, right? So you can study the inside of construction material when water is going through asphalt or concrete. You can see this with neutrons, or how water is taken up by the root system of plants. Another topic that is very discussed a lot is to do like protein crystallography, but with neutrons instead of X-rays. And this has been difficult so far. But it would be highly beneficial because you don't only see, let's say, the carbon structure and so on. You can also see what's happening with the hydrogen and so on. So this is a very important field. Another one is the energy-related materials, where a lot of batteries, fuel cell, hydrogen storage involve exactly hydrogen and lithium, light elements, which is highly beneficial to study with neutrons. The other field, as I say, neutron scatters and can detect magnetism. So you can really, it's the only tool really that can tell you a detailed spin structure of the magnetic spins in a material. And this has impact on many, many different fields. I have one example is electrical motors and generators. So if you can understand and make better magnets, the motors will be much more efficient. Another hot topic that, that was mentioned many times the last few days are that we are using a lot of energy on computing. So there was some articles about server halls and how much they are actually consuming. And if we could replace today's electronics with much more energy efficient spintronics and quantum devices, this will really, really help a lot. This is a very important field for neutrons. Two other is isotope sensitivity. So you're sensitive not only to an element, but the different isotopes of the element. And this means that you can do contrast and labeling. So if you take a molecule and when you produce this molecule, you use different type of chemicals with different isotopes. You can basically earmark or label different parts of this molecule. And if one of these isotopes is, let's say, more visible than the other, you can try different isotope labeling. And from that, you can deduce which part of the molecule is active in the dynamics or structure, for instance. And this will help you understand, let's say, catalytic reactions and molecular dynamics much better, because you can tell really that, oh, if I isotope label it like this, I see something, or in the other case, I don't. And then you know that, let's say, this part of the molecule is active in this reaction or process. So this is very, very important part for neutrons. Another more general thing is that neutrons, they're neutral particles, so they are highly penetrating. So you can really measure bulk of a material or a device. And of course, you can measure surface as well, but it's highly penetrating. And this means that, for instance, you can actually build very complex sample environments. So a big chunk of metal and things that you build an oven or a furnace or a high pressure device, and you can actually go through that device and into your sample that is inside and still measure it with neutrons. And this means that you can go to higher pressures or high and low temperatures or very high magnetic fields and still measure it with neutrons. Another benefit with this is that you can also do in situ in operando studies. For instance, you can look at the motor while it's running and you can see what's going on inside. And for instance, in this case, you would be able to see the fuel injection in this motor while it's running from outside. This would be impossible by X-rays. It's completely impossible. And for instance, for energy sector, you could actually put a whole battery device inside. And if you make it in the right way, you're able to actually look at what the atomic structure is doing and the dynamics of the ions in this battery while you're charging or discharging your battery. So this is a huge benefit. So of course, Sweden would like to take advantage of this as much as possible. And when you discuss building community, usually we start at my last point here. So we're saying that, yeah, we're investing a lot in this, so we need to build a community. Sorry. However, I like to start on the other end and say that, as I already show you, it's a very flexible technique, and you can do things that you can't do with other techniques. And to use neutron scattering will be highly favorable for Swedish academia and industry. And that's basically the reason why we should go in this direction, I think, and strengthen the large-scale community in general in Sweden. Specifically for neutron scattering is that we had the neutron source back in 1960 to 2005 in Studsvik. And let's say the real pioneers and experts in Sweden right now in neutron scattering, there are a few exceptions, but the real pioneers and experts really belong to this generation. And unfortunately, they will actually retire before or just after ESS comes online. So we need to ensure a future sustainability of this community in Sweden. And that means scientifically, technically, and politically. So we need to have all these factors in the community. And we will lose a lot of this when these people retire. And then, of course, we are investing a lot of money. So, of course, we should take full advantage of this. We have given an opportunity. So how do we actually maximize this output? Of course, we can extend the community by employing PhD students, educating new experts, activate new areas that don't use neutron scattering before. We can, of course, that includes industry, and then recruit some key persons to Sweden, both in academia and industry. This is important. We can also strengthen the existing community that we have, and this means some targeted funding for strategic neutron projects. This is already going on from VR. Of course, we need to make sure that we have experimental time, beam time at the already running sources so that we can train and do science in preparation for ESS. And then, of course, we need to make sure we don't lose key people that we already have here, both in academia and industry. And then finally, we need to be active in the ESS involvement. So being a strong host country, this is very important because we need to guard Swedish interest, that the ESS becomes a facility that's good for Swedish research. Of course, for all research, but in our case, we want it to be good for Sweden. So we need to take part in this and take credit for what we are doing. So this is important. We are too modest in Sweden. So on educating students, so I'm here, I just wanted to correct to say that I'm the study director of the Svenne School. So the managing director is Martin Sahlberg in Uppsala. So just to make that correct. This is a national school for neutron scattering graduate school. We have 40 fully financed PhD students, 20 of them are already hired, as you can see, and we are hiring another 20 soon. And this is fully financed by SSF, 220 million. And we have these 6 participating universities, KTH, Linköping, Chalmers, Stockholm, Uppsala, and Lund. But the whole school and course catalog, this is open and free for everyone, including academia and industry. And we have so far educated about 500 participants in our courses. We have 9 different courses from intro level to specialized courses. And we also organize this annual Swedish Neutron Week, where I showed you the picture on the first slide. And at this Neutron Week, we have both students, a lot of students, but we also have directors. So this is a bunch of who is who in both Sweden and international and funding and so on. And we have a lot of directors. And just a small note is that among the directors, we can see this 14%. This is number of women here. And on this slide is 50. So we are going in the right direction also for the neutron community. So how are we doing? Well, Sweden is doing quite well. We had originally estimated 2% usage of one of the biggest sources in Europe, ILL. And this was an overestimate, but we have steadily increased. And right now we increased by 350% the last 15 years, especially after the decision for ESS. So we increased now up to 5.5%, and similar number is for ISIS actually. And this makes us the same size as Spain and bigger than Switzerland and almost 3 times larger than Denmark user of ILL. So this is very good. And the same thing on the publication, we have increased the last 10 years quite steadily. And the same for the community, where we actually at some point we were declining and we were smaller than Denmark, and now we doubled actually the last 5 years. So this is going really well. And we need to keep in mind that if we are supposed to pay 10% of the running cost, we are supposed to use 10% of the beam time at ESS, right? So we need to keep building. So a few examples of Swedish highlights. We have Wallenberg Wood Science Center and collaborators that work on bio-based materials. This was an example where they made thin films on nanocellulose and spray coated and see how humidity affects this. This is very nice work. We have an industrial project, AstraZeneca, looking at nanoparticle and drug delivery system that was 2 years ago published, and they keep doing it. We have one case from Chalmers where they look at energy materials and protoconductors for new fuel cells. There is also neutron-related results where efficient neutron supermirrors are made at Linköping to actually improve even further the ESS, let's say. There is a KTH, other universities, and industrial collaboration concerning steel, so engineering materials, where they saw that with different heat treatments, they can actually make the steels better, so less brittle. It's a very recent publication. And just one example from my own research to connect to the quantum materials, where we have discovered new quantum states in new materials a couple of years ago. So we are covering a very broad field. And I'm running out of time, but I will try to quickly wrap up. But what is very important is that ESS is clearly a world-leading neutron facility. It will be the best. And this means, of course, you often see this, that you have a higher production of neutrons than any other source. But we will also, on the other end, detect and take care of the neutrons that we produce much better. So the effect is more than double, let's say, not only that we produce, we will also use them. And all the 15 first instruments will be average 20 times better than any best instrument existing, but some 250 times better. So this means that what we now measure in 20 days or 250 days, we can measure in 1 day, roughly. So we can measure much faster and study much smaller samples. And this is really a game changer for many fields. For instance, protein crystallography, quantum materials and energy and so on. And the same for in-opera understudy, because the high intensity give us time to slice things up, not as fast as XFEL, but we can do much better in situ in-opera understudy. And the same for extreme conditions, that we can push the limits to go to higher pressure and higher temperatures and so on. And it's really a completely new world to do science in such a facility. And we have the existing best sources, let's say JPark and SNS, gives us a teaser on what we can do. And I have my last slide just to say that what were we doing right now, Sweden and ESS, is that we are involved in several ongoing projects related to, let's say, technical developments at ESS. And this is mainly sample environments, for instance, at the Bifrost, Beer, and Freya instruments. But another point that is often forgotten, or I would say always, is that a lot of work is done by Swedish researchers preparing for first science. And this is not visible, because this means synthesizing sample, making initial characterization, doing the pre-study with neutrons to be ready when ESS comes online. And this is very, very often forgotten, because it doesn't look like you're contributing directly to ESS. But you will contribute by this to the first science. So it's very important. And then, of course, there are many things we can do. We can collaborate nationally. This is very important, because we have to compete with the best scientists in the world to get time at the best neutron source in the world. So we cannot, we have to involve the entire country, not only Skåne, but remember that neutron scattering in Sweden is not only ESS, right? We have to collaborate. And a very important point also is to avoid output bottlenecks, so that we will get a lot of data, but to match this, to not have another limiting factor, we need to be ready with good samples, modeling tools, and so on to understand the data. And of course, there are new instruments that will be decided, and a Swedish instrument project at ESS will be very good, I think. It will kind of unite Sweden a little bit and also help maybe Swedish companies to be involved in ESS. And there are some initiatives. And then finally, industry is very important. There is still some work we need to do there on basic information, what can be done, how, limits. And we need to encourage industry and academic collaboration, plus using RISE. And finally also, industry had to actually, if they want to take fully advantage of this, they also have to have a strategic long-term competence investment, especially with larger companies that can do this to take full advantage and think ahead. This I've seen in my collaboration with Japanese industry, for instance. So with that, I thank you all for your attention, and go neutrons for Swedish science, industry, and society.
Okay, thank you, Martin, for this very interesting speech. And I have one question which I'm thinking about when comparing your speech to Filipe's, which you didn't hear. But my understanding is if you look at an XFIL, for example, you actually push the limit for how small object you can observe, and also in motion. And basically what you do then is also push the limit for, in a way, basic research. In a way that... So I understand that the ESS is a much broader facility, taking it from basic research and had the potential to be much closer to innovation and improvement of products and so on. So it should be a more attractive for industry, actually.
Well, I mean, in all fairness, I mean, I think Filipe agrees with me here that, I mean, the free electron laser was, let's say, it came from, let's say, nothing into everything, right? And everything was completely new. I think when they turned on the key of the first, they didn't know what to expect almost, because it's really an even bigger game changer, yes, for fundamental science. And I think there is, you know, it's been a huge development in that field the last years. And I think they are understanding more and more what you can and cannot do. And of course, this is applied to more fundamental science. But it will come, I'm sure. There will come things in applied science for XFEL as well. For neutrons, yes, it's a little bit more direct to see the usage. And of course, also, I mean, you have to remember that the number of beamlines at ESS, I don't know now the numbers, but the number of different instruments that are dedicated to different fields are much more than at XFEL, right? I don't know how many, is it, you know, 1 or 2 or 3 stations? I don't know exactly on the European XFEL, right? So it's a bigger toolbox, which also means that the field you can cover is broader.
Okay, and just one more question then, if you have time. I mean, basically you can say you use Max 4 and you could study, well, in a broad sense, heavy objects, or and you can use ESS for light objects, or at least in the periodic system then, if you say. But how common is it actually that researcher in their research process actually need both facilities?
Oh, so of course I was focusing on the benefits of neutrons in this case. Of course, you can study also heavy elements. So it's a little bit more complicated how the dependence on elemental number looks for neutrons than it looks for X-rays, because in X-rays, basically, the heavier, the easier, or the heavier you see scatter more. But so you can study both at ESS, but I think the complementarity in general with X-rays and neutrons is excellent, right? Because you have, let's say, measurement using photons will always be faster than with neutrons. It's just you can produce much more photons than you can produce neutrons ever. This will never catch up. But you have a different contrast. I think the word contrast is the best to use. Is that you see things differently.
Yeah.
And to combine X-rays and neutrons is, of course, highly beneficial. I do that very often myself. And I would say that I think it was excellent that you had Filipe here with Hamburg, because I would like to kind of add to that, basically Max 4 ESS and Hamburg with both XFEL and Petra 3 with the Swedish high energy X-ray beamline. This is really excellent complementarity between, let's say, these 3-4 sources for Sweden.
Okay, just a short question with probably a long answer, but how do we best prepare Swedish industry to be users and take advantage of ESS?
So yeah, I can, maybe I go back here. I mean, there are many things we can do, but I mean, I have worked in many, well, several at least, industrial related and collaborating projects, both using neutrons and X-rays. And I mean, there is still some work, and I remember Lena Ek said this, that when she talked to the companies, it was clear to her that it's still this question, what can you do, what are the limits? We need this basic information still out, and we need to get this through what you can and cannot do. This is very important. And then, as I say, within my collaborations, I think it's very important, it comes down to individual persons if the collaboration should work. So you need to have the right person in the academia, and especially the right person in the industry that is, let's say, not too low in the food chain and not too high, because you need to know, you need to be able to kind of get your will through, but at the same time, you still need to be able to actually participate. So I think this is two key thing, I think. Then, of course, it depends a lot if it's it's a big industry if you're talking about AstraZeneca, or if you're talking about a small high-tech company. This is very different what type of support you need. So we have RISE. There are some of these, how to say, small companies that are popping up now, or especially around the Skåne region, about helping industry to conduct and analyze data, for instance. But I think long-term companies also have to recruit, and some of them are doing that. And we are educating 40 students in Sweden, so hopefully some of them will be hired by the Swedish industry and can help. Maybe Elisabetta.
Yeah. So thank you very much, Martin. And that was a nice way of handing over the word to Elisabetta, I think. So please, Elisabetta, I invite you for your presentation.
Yes. So first of all, thank you very much for giving me the opportunity to speak in this very important meeting. So the title of my project, as you can see, is a multifunctional material for sustainable society, quantum and energy. So as you can argue from the title, my PhD project deals with the sustainable energy problem. So as you know, the energy production and consumption is the major contributor to the man-made greenhouse gas emissions. And of course, as you also know, the most of this energy is actually wasted. So the scientific community worldwide, both in academia and industry, is trying to attack this problem from three sides. So by studying more sustainable energy harvesting systems and also more efficient energy usage system, as well as more capable energy storage devices. My very little contribution to this extraordinary work deals with these two latter aspects. So what I do is I work with condensed matter physics and material science in the characterization of novel material with maybe suitable properties for potential future application in battery devices or future spintronic devices. So of course, it would be highly beneficial if in the same material we could have both these properties. And this actually happens in a category of material that we call multifunctional material, where the discriminant is actually the temperature. So these materials have good diffusion, ion diffusion properties in the high temperature regime, so which means that the ions, they have high mobility, the ions inside these materials. And as you know, this is important in battery applications because the lithium ions, for example, in batteries, move towards the battery if when we charge and discharge the system. Of course, we would be interested in more sustainable kind of batteries, maybe replacing lithium with sodium, for example, or potassium or other similar atoms which are more sustainable and more easy to find. Then the same material we cool down at cryogenic temperatures. And what we are looking for is quantum properties. So in particular, we're looking for magnetic ordering. So the electronic spins of the atoms in a lattice of this material at low temperature order and create some magnetic lattices. So some sort of periodic structure of the spins that align in a certain way. And this would make these materials very, very suitable for spintronic application, for example, in magnetic memories, so some sort of data storage devices. So the same material, high temperature, suitable for batteries, in low temperature, suitable for spintronics. The materials I work with are spinel transition metal oxides. This is very general definition. I will focus on one specific example of multifunctional material, which is this sodium chromium oxide. So this material, just like diamonds, needs high pressure to be synthesized, to be made. So this is our group when we went to Japan to visit our sample provider. So this is the person that makes these samples. And he showed us that in order to make this much of sample in one synthesis process, it needs this much of a press. So it's a very complicated synthesis procedure which employs big machines to give very small samples out. But despite of the size of the sample, this one is very of fundamental interest for the applications I mentioned before. Indeed, this is the crystal structure and a model of the crystal structure of this material, and the blue and orange balls represent the chromium atoms, and the yellow ball represents the sodium atoms. The chromiums arrange themselves in the lattice in a way to create these hexagonal one-dimensional channels that are more visible here. So we take the crystal, we rotate, and this is what we see from the side. The sodium ions sit in this one-dimensional channel, which we believe is a privileged direction for ion diffusion, so suitable for batteries. Then the chromium atoms themselves arrange in these double chains, like some sort of zigzag ladder along this one-dimensional channel. And this particular arrangement of the atoms will lead to magnetic ordering at low temperatures, so suitable for spintronic devices. So this is, for example, a multifunctional material. So I measured this sample with neutrons. And why do I use neutrons? Well, because of course, as Martin explained very well in the previous talk, neutrons are a probe for structural characterization, just like X-rays, but they have better contrast for light elements. So in a battery material, we are looking for sodium, lithium, which are light elements. So this makes neutrons a better probe for the structure of battery materials. Then, of course, from the point of view of the magnetic ordering, neutrons have spin, as also Martin explained. So this interaction of the spin of the neutron with the electronic spin of the of the atoms in the lattice allows to directly extract the microscopic magnetic structure and the dynamics also of the spins. And the neutrons are actually the most direct probe for such kind of investigation that can determine completely the magnetic structure and also the size of the moment. Then, of course, we investigate from the structural point of view the diffusion properties of the ions, and we often always actually we combine neutrons with another technique, with muon-based technique, which can be only found in large scale facilities actually. So let's look at some actual data. So this is a series of diffraction patterns of sodium chromium oxide made with neutrons. So this is a neutron diffraction pattern as a function of temperature. So at low temperature, we are here. And then, as you see, as the temperature increases, the structure here changes quite dramatically. So this big peak here disappears. And this is related to the magnetic ordering. So just because the sample is cooled down to cryogenic temperatures, the spins of the chromium align in this way. So I made this model out of this data. As you see, this is the same orientation of the crystal that I showed before. Here, the sodium atoms are missing for clarity of display. And as you see, the spins of the chromium atoms align in this zigzag, let's say, fashion. And here, if you rotate the sample again, you can see the ladder that I mentioned before, with the chromium atoms arranged in this way, which makes it possible to have such kind of magnetic structure. So such a well-ordered magnetic structure makes this sample suitable for spintronics. Then high temperature results, again, here is neutron diffraction data, which I fitted with some Rietveld refinement. This is a fitting technique that we use for neutron diffraction at high temperatures, so 300 K. From this data, together with computer modeling, it was possible to determine the ground state of the energy potential of the system to find a possible diffusion path for the sodium ions. So as you see here, this is, so you take the crystal, you rotate, so we imagine to be in the plane where the sodium atoms are. This is the one-dimensional channel that the other atoms form. This is where the sodium atoms sit. This is the oxygen, this is the chromium. And we propose a possible 1D sodium diffusion path in which the sodium jumps in these interstitial sites and back in the actual position. So the sodium atoms do this quasi one-dimensional, let's say, zigzag diffusion pattern, which is highly anisotropic, which is good for battery applications. Then we complement these results with neutron data, with muon data, so which from the muons is possible to extract directly the hopping rate of the sodium. So let's say some quantity that relates to how mobile are the sodium ions in this lattice. And it also gives important parameters for the diffusion. So we see that the sodium atoms in this lattice have quite good mobility. So again, suitable for batteries. Then I belong to this graduate school in neutron scattering, as was introduced before. So I go to large scale facilities all over the world in order to measure my samples. And these are the actual amount of days I was awarded for beam time, so for experiment. And I went there to measure my samples. And such kind of research allowed me to build, of course, quite, I would say, good knowledge at the moment for this kind of large scale facility techniques, but of course also a very wide collaboration network, both with academia, with very prestigious university, as well as in industry, of course, in the facilities themselves. I mean, I think I know everyone in these facilities right now. And all this know-how just comes back to Sweden, where I have collaboration with several universities and research institutions. So I am one element of this new young neutron community in Sweden that is being built now, and that's just thanks to ESS coming. And by the way of collaborations, right now, in this very moment, I am at PSI, so this large-scale facility that is located in Switzerland. And this is part of a bigger collaboration also with Chalmers University. And it's funny because I came here, I am supposed to be here as a part of my PhD because I will be part of the team that is actually commissioning CAMEA. CAMEA is a novel neutron spectroscopy instrument, which is based on a very new idea. This is the first instrument of its kind, and the idea behind the CAMEA will be the basic idea for Bifrost, which is one of the first instruments that will come online to work in ESS. And it's very special for me to be here because I came here as a student. Here I am during my second week of PhD, just for educational purposes. I didn't even know what sample means. And now I'm here as some sort of expert to help with the development of a novel instrument that was never done before. So which will be this technology, this knowledge I will bring to Bifrost, of course. I mean, we will try this one and we will see the failures, the problems, everything that goes wrong. And this will be just beneficial for ESS at the end. So in this beautiful scenario of research and international collaboration, what does ESS actually add to my project? Well, of course, the proximity of ESS to my house make it practically more convenient for me, of course, to travel to go for experiment. But from the point of view of the science itself, as explained also before, I mean, this facility is extremely powerful and up to date in terms of technology of any kind. So it will make it possible to measure small samples like mine in a reasonable amount of time. It would be possible to measure samples in extreme conditions because this very large amount of neutrons that are coming can be collimated very precisely in a very thin beam. So this will increase, of course, the resolution and will cut away the background. So there will be very, very high quality data, which means that we will be able to observe very, very subtle things very subtle transitions and physical phenomena happening in our materials that is not possible at the moment, because if you don't have the resolution to see it, you would just not see it. So, and of course, this will make it possible to do inoperando in situ measurements. So, which for industry, for example, you have a device, battery or magnetic memory there running, and it's possible to measure while it's running. So this is something with high resolution. This is something which at the moment is not possible in other facilities with such a good outcome, with such good quality data. So for the very nature of my project, which is a little bit in between industry and academia, this makes ESS very exceptional facility to go to work. And not only for me, I mean, all the Swedish researchers will benefit of the ESS. So, and this is for Sweden, but of course, ESS is a big attractor also for the global scientific community, which will bring in know-how and world-leading scientists and brilliant people to Sweden. And this will make Sweden our leading country for research and development, both in academia and industry. So at the end, I believe that this was a very good investment of taxpayers' money. Thank you very much.
Thank you, Elisabetta.
I plan to ask the question, how ESS will improve your research possibilities in your research, but you already answered that.
Here.
So thank you very much for that. Another short question is that you pointed out the many different sources you use in your research.
Yes.
Are you using them because they are complementary, that you need to use different sources, or is it just as it happens where you manage to get time or so on?
It's a bit of combination of the things. So the different sources have different capabilities and the different kinds of beams. So you have somewhere pulsed beam, continuous beam, and depending on the type of conditions you have, you can measure certain things. So we apply, for example, at PSI, there is a beamline that allows measurements, muon measurements in high pressure, for example, and or with the low energy mu-SR, which doesn't exist anywhere else in the world. So you apply there if you have on the science itself that you want to probe. And of course, depends also where you get the time. So there are some doppelganger sometimes in different facilities. So maybe you submit the same proposal in both, and the one that if you manage to get the time in one, then you give up if you get the time also in the other one, you give up the time in the other one. But it depends very much on what you want to measure and how, and who gives you the time.
Okay, so very shortly, even then when ESS is up and running, you will need to use other sources for some specific research still. It will not.
Well, actually, if ESS builds all the instruments that they are planning to build, probably not.
Okay.
Then at the end, it would be just a matter of time, that if you manage to get the time, because it will be super high competition at that point.
Okay, thank you. That's a very good answer. Now we have a bit of a technical problem which you probably is aware of. So I will just say something to the general public. So I will turn you off, and then I will give you specific questions, and then you will answer. But then we will turn off our mic, so it will not be really the panel discussion that we have envisioned. So.
Okay.
So I'm not really sure how this works now, but I will ask some questions, and if you have questions, the audience, please send them in, and I will try to read them to the panelists, and hopefully they will give you wise and good answer to them. So can I start with a very tricky question? I think from my perspective, it is really tricky. And that is really all these research infrastructure facilities that we're talking about. They cost a lot of money, and they tend to increase. The cost increase because they become more and more advanced, and it's not just only within the area we are talking about here. So can we find a way of saying, basically, what parameters should we use saying that now this costs too much? Because I think it will never cost too much for science. So what other parameters to judge the costs for big research infrastructure should we use and rely on? Easy one.
Easy one.
Who is it directed to?
It's directed to all of you.
And I can start if.
Okay, Filipe will start, but then you will not hear his answer, I guess.
Well.
Okay,
well,
start.
Okay, so I would say that because of the because all of the growth in the economy comes ultimately from technological progress, it is very, very hard to put a price on technological progress. So I can't really give a value to research, but it has to be very high because it is what pushes us forwards and what makes ultimately the economy grow, I would say.
But if you have the money within a research system, then it's always alternative allocations. That is
exactly.
And that's our problem.
So you have to see the competition between the different research opportunities. I guess that's probably the way to put it.
Can I add something then? So, do you hear me?
Yes. Yes.
Okay, good. No, I agree with Philip. Of course, there has to be a limit at some point, but it depends on how you see it, because of course I see, and I think many people see, ESS is more like it's an infrastructure project rather than there is science, of course, but as a cost of producing it is an infrastructure project, right? Where the money actually goes back into the system in a sense that Skanska is building buildings, and companies in the countries are supplying high-tech equipment and so on and so forth. And this in turn, of course, also creates jobs. So it's a different type of investment than giving money to a scientist to do science, I think. So then, of course, I agree that the science that comes out in itself has a economic value, of course. Not with that said, if I try to take off my scientist hat and put on more, let's say, a Swedish citizen taxpayer hat, then of course this should be highly monitored, obviously, what this money goes to, that used in the best way. But to say where the limit goes, I don't think we can answer this. I don't have a better answer. It's not. It was an obvious question, but it's not easy to answer.
Of course, it's difficult, but it is a question that we have to. The fact to give an answer to over and over again, because we are in a system with limited resources. So I also think we need to really take it seriously, and I think this discussion we have here is really good also to try to show the broader usage and the broader importance of these facilities.
You shouldn't never forget that it's a tool, right? It's a technique to do something with. So it's a means to an end. It's not. There are certain aspects of neutron science, of course, also, but now we're talking in the sense of using them for doing science. So of course, it's an investment that is available to all if you choose to use it. And that goes for all the large-scale facilities. Once it's there, it's not that I'm not, unless I'm an industry that wants to make a patent, I'm not paying for beam time from my scientific money. So it's, and actually I would like to add one thing, and this is actually quite funny because I talked about in-house laboratories and so on. And what's going on right now in many universities is actually that you're pooling all these in-house labs into a park of equipment that you can apply for time or book. So actually, even the let's say universities are going more towards let's say large-scale thinking in the sense of having equipment as well. So I think this is probably anyway the way to go.
I'm totally agree there. And if I would try a metaphor, saying if a country wants to be a naval power of global impact, they need an aircraft carrier. And you can see ESS and XFIL and MAX-4 like the aircraft carrier. But it would be really good if you could try to also give a description of this, because you need the destroyers, you need the shipyards, you need the harbors, you need everything. I mean, when you build these facilities and you put a lot of money into them, of course, I think it's important. That's my understanding, at least. The importance to understand that you need a whole kind of a system around them, and also going back to say to the question which I posed in a very not so clear way earlier, but basically it's the system around them and what's needed in labs and pre-studies and so on. And if you could expand on that, please. And also the more specific question, how often is the case that you have a research project which basically you have almost the same type of sample to answer the same research question, but you need these very different facilities. So you basically go with the same sample to XFIL and ESS and so on. If that happens at all, or if it's common, or if you envision it will become more common in the future. So,
Philip, you want to start?
Okay, I can start. So I would say that there is definitely a complementarity of infrastructure. For example, very clearly between MAX-4 and the European XFEL. And you can see even in terms of techniques, for example, I presented the case of the serial crystallography, nanocrystallography that spreads out from the European XFEL to now to MAX-4, where it's developing a beamline for doing that. And also the researchers then use different techniques, but also not just MAX-4, also even in terms of ultra-fast lasers, they're also used in in-house facilities, femtosecond lasers to do optical experiments, and then you need some other tool to probe some other aspect, and then maybe you do go to the European XFEL to probe some other aspect of your ultra-fast phenomena. So that absolutely happens.
Yeah, I mean, I can just fill in and basically refer to Elisabetta's talk, because I mean, we do that all the time. I mean, really all the time. And sometimes it's even that becomes a factor, because you actually need the sample that you had in a neutron source in another neutron source, and it's active, and you know. So definitely we are doing this. And I mean, I spent 7 years in Switzerland, and a lot of time, partly officially at PSI, but also a lot of time when I was officially somewhere else. And there, I mean, this is exactly what you want. You have the Swiss light source, the Swiss neutron source, the Swiss muon source, the Swiss SFEL, the free electron laser, and you just bring your samples between these. You walk between them and do your different measurements, plus that you have all the expertise that both gives you ideas and can help you with this. So, I mean, when I left Switzerland, coming back to Sweden, everyone congratulated me a lot that I come back to this type of environment where we are building up these facilities. And I would like to add one more thing, partly to this, but also to partly your previous question, this factor that, you know, how do you benefit from it and so on. And in J-Park, I think it's an excellent example. Now, Japan is a very different country than Sweden and Europe in general, but there, you know, the local region, so that would, the Ibaraki prefecture, for instance, that would be like Skåne in Sweden. They paid for 1 or 2 instruments at J-Park because this is beneficial for the local industry in that area. Just as an example. And of course, it's a little bit more complicated. J-Park is a national source and this is European and so on. But so this is where it's going, right? And when I was collaborating with Toyota, I mean, they are investing in beamlines both at the synchrotron and neutrons because they see that this is the long-term benefit for them. They have a 20-year development plan where they see that if they use neutrons, this will be highly beneficial for them, for instance.
I think the last thing you were saying is extremely important to understand that the long-term perspective in this, that we are not, it's not quick fix facilities. It's usually something you need to have a long strategy, whatever you do. But are you also saying, when you pointed out that the work is done, that is now carried out among the universities, that you build up a kind of an infrastructure park and so on, that also Swedish universities need to take a bigger responsibility for the kind of infrastructure landscape or system around the big facilities. So you actually can prepare researchers, both in education-wise and also in the exact projects that they're doing.
That was my comment on bottlenecks, in the sense that to take advantage of this, there are two things. First, that I think we do need to collaborate a little bit better, especially this is very highly area dependent in science, but there are some collaborative efforts that needs to be better in order for us to be competitive, to really get time at ESS in competition with all the world leading scientists that wants to come there. And the other part, my bottleneck comment, that yes, if we are, let's say, have good enough ideas to get beam time at ESS, but it doesn't help if we cannot have the sample, or we cannot, you have to come there. You cannot come with a sample you don't know anything about. That goes for any large scale facility. It needs to be well characterized. You need to know it's good quality. All this work needs to be done before. And the same thing after, when you get the data, to understand it, to analyze it, to model it, to have computer simulation that matches this. And I'm sure Filipe agrees with this, that if you don't have these resources, you will not take advantage of all the terabytes of data that you will get out of the ESS.
Okay. No, I absolutely agree. And for example, in terms of the computing, it's pretty important, and it was not recognized in the early days of XFEL research, for example, at the LCLS. It was recognized at European XFEL, which has an important data center, and also in terms of sample preparation, there is the XBI laboratory, which Sweden contributed to also, which takes into account with the preparation of the samples and characterization. So yeah, those are definitely important points.
Yeah, and I think one of the points here that is important also, because I think there is a big kind of expectation that we are investing in these facilities, and now industry will benefit from them in a very high degree. But I think it's very important to be clear of that most industry can only do that in cooperation with the academic system, because of the reason that that you actually said. You need to have the whole kind of process from the sample to the data management and analysis in the end. And I think that's very important to see. So we have to strengthen the cooperation between academia and industry if we want to have that positive outcome.
Comment on that, to say that one important factor, because to be honest, sometimes I'm a little bit tired of listening, because many people just say that, yeah, industry, they just want to do short-term measurement and get result tomorrow and patent and earn money. And I think this is absolutely not true. Yes, sometimes these measurements happen and you do this, but and also for smaller companies that doesn't have the budget for a whole development division in their company, of course. But the bigger companies have understood clearly that this is a long-term perspective, right? And but still, of course, they need to still see that it's worth it. And that's my comment on saying that they need to understand exactly what you can and cannot do and get help in the beginning. But this is anyway highly beneficial to have this collaboration. And also, to be honest, I mean, the time between and let's say gap between fundamental science and applied science and devices in companies is much shorter now and much smaller. I mean, our mobile phones, everything, this is super high tech that comes directly from, in my field of condensed matter physics. So Samsung or whatever company that is doing this, I mean, what is done on the fundamental scale and what goes into today's devices, the time and gap is much, much smaller. Okay. So this is an important factor.
That's very interesting to hear. And a very different question, which I think is very well adjusted to the panel, because we have a very international panel with international experience. So we are now host country of 2 big facilities. So and what can we learn when it comes to governance, financing system, and so on from other facilities? And we have from the Polish Institute in Switzerland, which is similar, and we have ELL and ESRF in Grenoble and so on. So, what's your experience looking at the Swedish system and looking at other countries, how they govern their facilities, and saying what can we take home?
Who wants to take that one? I mean,
from the point of view of the investments, the single countries in their own facilities, what can we take home from their way of handling the facilities?
Yeah, I mean, it's a big responsibility to the host country, for example, of ESS. And then we have the national source of Max 4, and can we learn from other countries how to govern that in a way so we basically maximize make a better return for Sweden and Swedish research, and also then not only thinking return for Sweden, but also actually provide the world with large world-leading facilities that will attract people to Sweden and researchers to Sweden. So if there is something obvious that we need to think of that others have thought of.
We should not be so Swedish. So this is, I had that in my slide actually. I mean, we need to, as you say, we are the host country, yes, together with Denmark for the data management center for ESS, if I put it like this. And I think we can take bigger place. For ESS, it's still under construction, and we have an opportunity there, I think. And we were, to be really honest, we were a little bit slow in Sweden. So when I came back to Sweden in 2014, it was only these pioneers and experts that really cared a lot, I would say. While the rest of Europe was amazed by Sweden, you know, taking on the ESS and Max 4. And when I came back from Switzerland, everyone congratulated me, as I say, when I left, and then I came home to Sweden, it was like nothing. This has changed a lot, first of all, for the much better. So now there is really a momentum in Sweden going in this direction. We need to keep this up. And we should not be scared to take place. Because you know that Sweden would put, you know, I wouldn't say pressure, but to put our interests really strongly, what we want the instruments to be able to do, what sample environments are best for Swedish research, what, all these details. I mean, no one, I would say, in the other European countries would be surprised if we did this more. I think they are more kind of wondering why we are not. So as I say, we are changing a lot. It's improved a lot. We are getting more and more involved, but I think we can get even more benefits out of that. So I say we are doing a lot, but you don't see it so much when you, let's say, see presentations from ESS maybe.
I would like to add from point from the European XFEL that I think Sweden actually is punching well above its weight in terms of XFEL radiation, as we once did for protein crystallography, for example. And we were involved since the beginning also because of the early history in terms of flash and in terms of the LCLS, and that has clearly paid off, I think.
Yeah.
No, for the XFEL, it's clear that it's paid off. I mean, we actually, from the research council, we experienced from another angle. Because the Swedish researchers are so successful at XFEL that the cost goes up extremely quite much, and then we need to handle that. And of course, then we are in a situation which is really difficult because we need to handle that within our budget, but we don't want to prevent Swedish researchers from doing really top-of-the-art research. So it's a tricky question to handle, but it's clear that we are successful, and XFEL is one of these facilities that we had made really progress and contributed a lot to Swedish research, so definitely so.
Can I add one thing to that, just to say what we need to do? And I think we have actually a very good opportunity in the sense of that we have Max 4 already online. So, I mean, the whole, let's say, culture and community and collaborations and so on, since they are highly complementary, these techniques, to have an overlap between these facilities, of course, you need to understand that one is a national source and one is a European source, and this makes certain things difficult. But to use that Max 4 is already up, and if you want, of course, also in Hamburg that we have this to use this as the breeding ground and training ground and start for what we will also do connected to ESS. I think this is a very good way, because then we will be up and running when things are going. And this was again my comment a little bit, that there is a lot of work going on that is connected to ESS, but it's not visible because it's let's say science that is preparatory, and then we are ready when ESS comes online. So I think this is very important. And as I understand, they are doing collaborating better and better between the teams, let's say at Max 4 and ESS, about considering how can you move samples between the facilities, practical things, right? Because if you can't move a sample from one facility to the other because it's a different radiation zone, then this blocks you, right? So, yeah.
I mean, definitely we need to come to terms with that kind of difficulties, because from the researcher's perspective, ownership and governance and so is a non-issue. Of course, they want to use the facilities, and that's that's our primary task, to make that happen and make it possible, I guess. Okay, we are closing into an end of this seminar, and I want to thank our speakers very much for contributing, and I think it was really interesting to listen to. And also I hope that the audience that we haven't seen, but obviously is there somewhere in the cyberspace, also have enjoyed the seminar. And I apologize for we having some technical difficulties and so on, but that happens. We are talking really high-tech facilities. And we try to make a really high-tech seminar. And sometimes you don't get all the way you think you're supposed to travel that day. But anyway, I hope you enjoyed it and so on. And there is still a riddle for you, and that is to figure out why all the people in Sweden have so funny clothes on the pictures.
People in Sweden have funny clothes.
No, on the pictures that Martin showed, you had the dress code was kind of
yes.
obvious. So otherwise, I have no opinion. So okay, but thank you very much, and
thank you
for your participation.
It's in the future to discuss more.
And I think this is a discussion that we need to continue for many years. And in fact, research needs facilities. I think it's obvious. We have the discussion on how to finance and governance that will follow all the time, because that's important. But it's also important to actually take the opportunities that they give for Swedish society, not only research, but for the society as a whole. Thank you very much.
Thank you.
Thank you.